All right, in Concept C, we're going to be doing a little bit more dimensional analysis, focusing on the actual equations that we've been working with. So chemical equations are just like recipes. We can double them, triple them, cut them in half, and we're basically going to use that idea when we go to do these calculations. So here we're given a reaction, a combustion reaction between methane and oxygen to make carbon dioxide and water. Now for this particular reaction, our recipe, it's going to take 1 mole of methane and 2 moles of oxygen in order to make 1 mole of carbon dioxide and 2 moles of water. But what if I actually had 2 moles of methane to burn? If we're doubling the methane from 1 to 2, then I'm going to have to double all the other coefficients. So in this case, if I double again 1 methane to 2 methane, I'm going to have to double everything else, meaning I'm going to need 4 oxygen, this will produce 2 moles of the carbon dioxide and 2 moles of hydrogen gas. Oh, that should say, I'm sorry, not hydrogen gas, but H2O. So if I had these 2 moles of methane to burn, again, everything gets doubled based on the original coefficients. So we can actually use dimensional analysis to determine the number of moles of reactants and products involved. Now, the one thing that we're specifically doing it for this purpose is this is going to build on top of what we did last week when we were converting between moles, particles, and volume, and we're going to be putting it all together in the following lesson on stoichiometry. So it might seem a little bit tedious to be setting it up this way, but there is a purpose behind it. So the first thing, we always have to work with a balance equation. So balancing this one, we need to put a 2 in front of the HBr, and then 1's go in front of everything else. Now, if I have actually 3 moles of hydrogen bromide to react, how many moles of hydrogen gas is going to be produced? So we're looking at changing the amount of HBr and then seeing how much hydrogen gas we're going to then produce. So just like our normal dimensional analysis, we're going to start with what we know. In these calculations, you have to include the formula of the compound or element that you're working with. So you have 3 moles of HBr. I then go and find that compound in the equation and locate its coefficient, which is a 2, which means that I have 2 moles of HBr in the reaction. And then I go and find what I'm looking for, which is hydrogen, and I take its coefficient, and I'm going to plug that into the equation. So that way, again, remember in our dimensional analysis, the amount above and below the line are equal to each other, and we're getting this from the reaction. So for every 2 moles of HBr, we're making 1 mole of hydrogen. So by multiplying across the top, dividing by the bottom, I find that if I start with 3 moles of hydrogen bromide, I'm going to make 1.5 moles of hydrogen. All right, now for another example, feel free at this point, if you feel like you have a good handle, to pause it and then come back and check. So balancing this equation, I'm going to balance out the zincs by putting a 3 there, the phosphates by putting a 2 there, which means I need 6 of our sodium acetates and then just 1 zinc phosphate. All right, so I'm saying now that I have 2 moles of sodium acetate that are produced. So instead of making 6, I only made 2. So I want to know how much sodium phosphate did I use or start with. So again, same idea. We're going to start with our 2 moles of sodium acetate. I then go and locate that compound up in the equation. I look for its coefficient out in front. That's now going to represent 6 moles of sodium acetate, which I place in the bottom in the denominator. I then go and find the element that I'm trying to get to, which is sodium phosphate and its coefficient. That 2 means that I have 2 moles of sodium phosphate. So for every 6 moles of sodium acetate produced, I needed 2 moles of sodium phosphate. So by multiplying across the top, dividing by the bottom, 4 divided by 6, we get 0.66 moles of sodium phosphate. And again, it is as simple as that. Again, tomorrow we're going to practice just this skill, but then on Tuesday we are going to move on and work on applying this to an even bigger problem.